All right, so this is video 5 of week 11 of CS 499 Network Science with Dr. Vigil-Hayes. So I know that inquiring minds are very curious to compare how these three different types of networks that we've been talking about, assortative, neutral, and disassortative, move through the four different network regimes. So remember we had subcritical, critical, supercritical, and then fully connected. So looking at the three network types, we'll start with the neutral network, since this is what we've already been looking at lots of examples of neutral networks. Barabasi Albert is a neutral network. Erdős-Rényi generates neutral networks. So if we look at this green line, which corresponds to neutral networks, we can see that the S to N ratio, and this is going to be the ratio of the number of nodes in the giant component relative to the total number of nodes. So we see that until we hit the critical point, so that's where average K equals 1 in the x-axis, S to N ratio grows very slowly. It's very, very low. You can't even see it growing. And then all of a sudden, when we hit average K equals 1, the S to N ratio grows very rapidly. And we very quickly move from the critical to the supercritical. So this is something that we've observed in several different network examples. So maybe more interesting then is to see how assortativity and disassortativity influence how quickly nodes kind of increase their S to N ratio as they go through the different regimes. So again, the critical regime is always going to be defined as average K equals 1. That's always going to be our critical point. What we might notice is that for assortative networks, which are shown with the orange line, our S to N ratio, so the size of our giant component, grows very quickly even before we hit the critical point. So even before the majority of nodes or the average K value has a value of 1, we still have this very large giant component. And then, after we hit 1, so after we get to the critical point, it still grows, but it's not growing as quickly, so as quick of a rate as the S to N ratio grows when a neutral network hits the critical point, right? So we have this gentler slope. It just starts a lot earlier in the process. So even back in the subcritical phase, an assortative network is really building up that giant component. Finally, with the disassortative network, so this is shown with the purple line, we have kind of the opposite thing happening. So we have this very, very slow growth in the S to N ratio. So the size of our giant component is really growing very slowly. Even after we hit the critical point at average K equals 1, we still have a very, very low S to N ratio. And then all of a sudden, at some point in the supercritical network regime, the S to N ratio starts growing very rapidly before it kind of tapers off in its growth rate as it starts to approach a connected regime. So, a little bit before average K of 1.5, all three of these networks really slow their rate of growth, especially the neutral and the disassortative networks. They really slow the rate of growth. But when we think about the rate of growth for the S to N ratio, especially when looking at the disassortative network, this should kind of make sense. So in disassortative networks, remember there's a preference for nodes to connect to nodes that have degree values that are unlike their own. So this means that initially, if you have, if you're growing a network from scratch, kind of like with the Zolvi, brunette, and oh my gosh, let's see, Zolvi brunette, and uh, we'll just call it the XBS algorithm that we talked about in video 4. So even when we're generating assortative or disassortative networks, so if you imagine we're starting with these nodes that have maybe a degree value, and in a disassortative network, they are going to not want to form attachments to nodes that are like themselves. What this means is that you might end up with these little islands, these smaller clusters of nodes, where you have a hub that's connecting to maybe a lot of smaller non-hub nodes, but you have this resistance for hubs to connect to each other, and you also have a resistance for low degree nodes to connect to each other. So for a while, you might have these, little subcomponents, a bunch of little subcomponents that, depending on how you're building your structure, might be repellent. Especially when you have a lower K value and you're maybe in the subcritical regime, they're going to be somewhat repellent from each other. Whereas with the assortative network, because you have this like attracting like situation going on, you're going to have these high degree nodes really seeking out and wanting to connect to other high degree nodes. So that means that every time they form a connection, you're sucking in a larger and larger portion into your giant component. So this topic would be an excellent topic to focus on for generating exam-like questions in our weekly check-in channel on Slack. It would be a great kind of topic to really reflect on, especially since we've talked a lot about moving through the different network regimes, and just as a way to really make sure that you understand, what does it mean for a network to be disassortative versus assortative, especially in the context of what we already know about neutral networks. This is a really good way to start thinking about that. All right, so that is the end of new content for week 11. So any other videos that I make are either going to be, diving into some of the how-tos on Network X, or it's going to be focused on clarifying any of the content that I've already covered in videos 1 through 5. So thanks for listening in, and I look forward to hearing your thoughts and questions.